Welcome to Embedded. I am Alicia White alongside Christopher White. Our guest this week is Dmitry Grinberg, and we're going to talk about Linux on microcontrollers, or whatever's smaller than microcontrollers, like itty-bitty controllers.
Pico controllers. Hi, Dmitry. Welcome.
Hi. Nice to be here.
Hey, Dmitry, could you tell us about yourself as if we, met on an airplane?
Sure. I'm a software engineer. I mostly like to write code for small systems. I occasionally have delusions of designing hardware. Sometimes it even works. And I like to write up my projects because I like to think that people sometimes will try to reproduce them and actually learn something from it. Sometimes people write to me and tell me that's what happened, and that's kind of cool.
And you have some really interesting projects. But before we talk to you about those, we want to do lightning round, where we ask you short questions and we want short answers. And if we're behaving ourselves, we won't ask, well, what about the networking system or other longer questions? Are you ready?
Bring it.
Favorite processor?
Probably one of the Apple Silicon processors, ARM64.
Favorite Linux distribution?
Debian, because it mostly just sticks to doing what it's supposed to be and not showing off.
How many bits is enough bits?
It depends for what. I could do a lot with just one.
How many bits is too many bits?
I don't play too much with 64-bit and higher. It's just too big, not much of a challenge.
KDE or GNOME?
Neither. I use XFCE.
Okay.
Complete one project or start a dozen?
I don't allow myself to have more than 2 projects in flight, because if I did, I would never finish anything. I don't consider a project done until it's finished and written up. So I'd like to start a dozen, but I don't let myself do that.
Favorite fictional robot?
Absolutely Marvin, the paranoid android.
And do you have a tip everyone should know?
Yes. If you don't know how to do something, find some corner of it that you kind of know how to do and then do it. That'll get you into the problem more and both motivate you and help you figure out how to do some other adjacent parts of it. Eventually, before you know it, the whole problem will be done.
Okay, I got to go write that down. That's really, really good.
It is a really good one.
And it applies to lots of things besides technology. That's very good. I like that.
Before we get back to today's discussion, I want to share a new resource for anyone curious about the rise of AI in engineering. Mouser Electronics has a dedicated Empowering Innovation Together hub that covers the latest breakthroughs in tech. Their new series explores how AI is reshaping engineering, from design automation to rapid prototyping and predictive maintenance. You'll find insightful articles, podcasts, and videos that showcase real-world applications across industries. If you're ready to see how AI is powering the next generation of engineering, head over to mouser.com/empowering-innovation. Now, let's get back to the show. We have been kind of skirting around small processors, and we mentioned Linux. So last spring, you posted about an 8-pin Linux project. And this was 3 chips that each have 8 pins. Could you tell us about it?
Yeah, so the idea was that sometime long ago in computing history, you could actually buy a kit computer that was comparable to the sort of computer you could buy in a store. But you could assemble this at home and have comparable computing power. We are very long away from that now,
Yes.
But I thought it'd be cool to try something similar. So for some definitions of modern computer, being able to run Linux and compile a C program can sort of qualify. So I tried to find the minimal set of parts I could use to produce such a computer that one could still hand assemble at home, assuming no soldering skill, which means only using very large chips with very few pins. And I built on some previous code I'd written to emulate MIPS and boot Debian on it. And then I designed a small board that is about 1 inch across, circular, with a USB connector on it that actually does all this. And if you assemble this at home, it will, over about a minute, boot, and you'll be faced with a command line with the real Linux on it that you can then actually write some code and compile it and run it.
So the Linux has, you mentioned GCC compiler and make, and then an editor, VI, right?
Yep.
But there's no networking.
No. So networking was something I thought about, but there was not much I could do with just chips with 8 pins, which was, of course, an artificial limitation, but that's what made the project interesting. So in order to interface to USB, the options are very few in terms of things that have 8 pins. It's either USB to serial chips, which is what I used, or you can use something like a 8-bit AVR ATtiny to bitbang USB.
Oof.
That gives you a few more options, but networking is not happening anyways.
So this USB to serial chip was one of your 3 allowed chips.
Yes, it was a really cute chip I found from Prolific. I'd never seen it before, but now I like it a lot. Basically, you connect USB to one end of it, serial comes out the other. It doesn't need any external parts,
Mm-hmm.
and it even will supply 3.3 volts for the rest of your project. It's actually pretty awesome.
Yeah, I've seen those on a previous project, and unfortunately, we didn't get to use it, but I was pretty excited that it existed.
And one of your other chips was RAM, right?
Yes, so Linux needs megabytes of RAM. If you're going to stick with text mode Debian, you can fit into about 8 megabytes. So I used an 8 megabyte PS RAM chip. There's actually a bunch of them out now. They're pretty convenient for all sorts of projects. They're made by AP Memory in the US, and in China there's a company called Vilsion that also makes them.
And an SD card, which isn't counting against your chip count.
Well, I don't think it's a chip. It doesn't have legs and you're not soldering it. So I think that's a fair excuse.
That I will accept that, yes. And now the big question. You actually, in your write-up, did an analysis of half a dozen, almost a dozen microcontrollers with the pros and cons. And I have to admit that I have a little bias concerning the PIC 16. And so I loved your analysis. Why was that not suitable for this particular project?
So the annoying part about PIC-16s is not very performant at all. So I actually started my microcontroller project programming long, long ago with PICs, and I was a reasonably big fan of them at the time because they could go relatively fast at the time. But now we have ARM microcontrollers that go much, much faster. PIC-16 will go at 32 megahertz, which doesn't sound terrible until you realize that it takes 4 cycles to do an instruction, so you're down to about 8 million operations per second. But then it's also an accumulator-based architecture, so even moving a value from one location to another is 2 instructions, and God help you if you need to actually do something with the value. So before you know it, you're going really, really slowly. That, and even though there is a C compiler for these, it doesn't produce very good code. It can't. This architecture was never designed for C. It was designed for being programmed in assembly, which is fine. I've done plenty of assembly programming, but even assuming I wrote my MIPS emulator in assembly, the other options were a lot more performant. And my goal was not only to have this thing be small, but also performant enough that I could claim it's interactive with some degree of being honest. And I don't think that could be done on that PIC. But I did fairly evaluate every 8-pin microcontroller I could find.
Yeah, including an AVR, which you've run Linux on before.
Yes.
But you didn't think that would be interactive because the boot time on that was a little long.
Yeah, so first time I did this was 6 hours long because I wrote it in C. If I did it in assembly now, I could probably get it down to 2, but that's still a lot. I mainly chose the fastest thing that had enough useful pins. You'd be surprised how many manufacturers make an 8-pin part and then do completely stupid stuff with actual pins. Like, if you're making an 8-pin part, there should be one supply pin and one ground pin.
Mm-hmm.
Why would you have 2 supply pins? Why would you waste an extra pin out of your array of just 8? I don't know. And yet that was really, really common.
And then you determined you needed one MIPS of CPU. How did you make that determination? Is it a Debian thing?
No, I mean, there's no official requirement. I mean, if you on my other projects, I booted Linux at 74 hertz. That was basically me trying to evaluate how fast it would need to boot in order to boot within a few minutes so a user doesn't get bored,
Okay.
and so that VI is interactive enough that you're not annoyed using it. And I just evaluated it by trying. I literally made an emulator for MIPS a while ago for a different project, and I was able to slow it down on purpose on my PC and come up with that approximate number.
So this MIPS emulator, we are okay. Maybe take me through the boot process, like from the reset vector. I'm on an ARM processor, and I've hit the reset vector. And normally now I would be doing the cinit,
Yeah.
and then going to main.
So most of the same thing. There is C in it, and you go to main. Main will then just load the first sector from the SD card into the external RAM, and then it'll start a MIPS emulator. And the MIPS emulator sees the external RAM as being its only RAM, and it jumps to the beginning of it. The code there loads the partition table and looks at it to look for a partition which is marked with a particular type. I think I used type BB. It then sees which sectors it contains and loads those sectors into RAM. Then that is the next stage bootloader, which then looks at the partition table again, finds which partition is marked as active. Actually, this one is much bigger, so it has a file system support. So it mounts it as FAT16, finds a file on there called VM Linux, parses as an ELF file, loads it properly into RAM. Then it looks for a file with clock in the name, and that it's used to figure out how fast the CPU should be running, since I'm overclocking it, and I wanted to give people a chance to decide how fast. And after that, it just jumps into executing the MIPS code in Linux kernel, which will then come up, and eventually it'll load partition number 3, because that's what the command line says, as the rootfs, and then you're just running MIPS Linux.
Okay, so this clock file, I want to separate between the MIPS emulator and the
bare metal,
the C running bare metal.
Yeah.
Does the C running bare metal, it has access to the file system?
Yes.
And so it has something like TinyFS or some other fat file system?
Yeah, so a very long time ago for a different project, I wrote a very tiny implementation of FAT16 that only supports read-only and needs about 9 bytes of state. That's what I'm using.
Wow. That's a cool idea, read-only. It saves a lot of headache.
It really does.
Exactly. If you're clever, if you're using an SD card, because it's SPI and you can pause the clock anytime, you can get away without even having a 512-byte sector buffer. So this was used when I was writing a project to play audio from an SD card on a microcontroller with only 128 bytes of RAM. The idea is you can start reading a sector, get to the byte offset you need, and read it. If the next offset you need is further, you just keep going. If not, you keep going and skip to the end, then start it again. It's slightly inefficient, but you can get away with only having 9 bytes of state.
Sorry, my brain is whirling about that. And so then you read this clock, and you have to go to the bare metal for that, because that needs to access the chip registers for this particular microcontroller. And then after that, you're all in emulation.
There's a few steps here that I guess I sort of skipped over because they're not relevant to the emulator. But there's also a bootloader on the MCU in order to allow me to update it, since there's no debug connection that's usable, not enough pins. So in order to allow people to update it, there's also a bootloader, which also mounts the SD card, looks for an update file, and if it finds one, will apply it. Then jumps to the application that we discussed. It'll work without the bootloader as well. It's not an integral part. It'll just be very, very difficult to update if you wanted to change the emulator or fix something.
You just need a JTAG. No, you wouldn't just need a JTAG unit, because this processor doesn't have... How would you update it?
Well, so there's only 8 pins, which means there's not enough pins to do everything. So to allow me to debug it, I do have an SWD connector here. Mm-hmm. And when the processor starts, it waits for about 6 seconds before doing anything, and including reconfiguring those pins. So if you attach a debugger within the first 6 seconds, you can debug it. But this board cannot boot with the debugger attached, because the debugger will mess with the other uses of those pins. So initially, debugging I did over that. But now Basically, you can only update it using the SD card. You put a file called update.bin on the SD card, and a particular byte offset is a version number. It's compared to the current firmware's version number, and if the one on the card is a higher one, it'll be copied from card into flash, and then a reboot will happen. So you can update it that way. No debugging. Most you can do is output serial console out through the serial port.
I want to take a little step back because we talked about the emulator history of Linux stuff. Like you said, Debian runs in text only with 8 megabytes of RAM. When I first started using Linux, it was a million years ago, on a 486 with, I think, 8 megabytes of RAM, something like that. It was very small, but that was as big as Linux got back then when it was first came out. Long way around to my question. Use a MIPS emulator. Why is that architecture the right choice for something like this?
Well, so 2 parts to this question. One is why use an emulator at all, since Linux technically supports ARM.
Good to answer that, yeah.
The answer here is that my RAM is not real RAM. It's an SPI device. It's not actually in the address space of a microcontroller. Okay. I can't just read and write to it. So things that Linux expects, like let's allocate an 8 megabyte buffer or a 2 megabyte buffer, that's not going to happen. Because of that, we can't run Linux natively. We have to emulate to basically make this fake RAM look like real RAM. Every time an emulated device tries to do a memory load or a store, I can actually issue an SPI transaction. But why MIPS? I guess I should have made a table for that too. I didn't. But basically, if you have to emulate, there's a few choices you can use for what's properly supported by Linux. You're looking at x86, ARM, MIPS, and RISC-V nowadays. Almost everything else is more or less not properly supported if you want a real kernel and a real file system. x86 is a giant pain in the ass to emulate. Just decoding x86 instructions properly is enough to make a man go mad. Yeah. And then there is all sorts of other arcane stuff you're going to have to support. So that goes out the window right away. Next up is ARM. So I've done ARM before. My first attempt running Linux on AVR was ARM. But emulating ARM is also slightly tedious because all instructions can be conditional. And what that forces you to do is constantly be evaluating that condition. That slows down your emulation. Because before you get to the guts of emulating the instruction, you're first forced to evaluate if it should execute or not. Great for actually writing code, annoying for emulation. So that leaves us with MIPS and RISC-V. Those are quite similar in design, but RISC-V designers did one really annoying thing for emulation, is a lot of immediates. So the values in instructions are not continuous in the instruction. They're split over some bits here, some bits there. It makes it convenient for making a hardware implementation of RISC-V, but very annoying for emulation, because now in order to assemble this immediate value, you have to AND with one constant, AND with another constant, shift and add. I just described 6 instructions that I'm doing to get this immediate. Whereas in MIPS, it's always the bottom 16 bits. One single UXTH or SXTH instruction, and you've got your immediate. And when you're trying to go fast, every cycle in the emulation counts. So picking the architecture where I can get the value out 4 cycles faster matters, which is how you end up with MIPS. Plus, it's still quite well supported by Linux kernel and by Debian user space, which is kind of cool.
But part of that emulation is some sort of hardware abstraction where you mentioned the RAM needed to be, I'm going to say translated, wrapped, and I assume the SD card interaction and also the serial port?
So you emulate not just a processor, you emulate a machine. Linux doesn't support just processors. So the machine I'm emulating here is a DEC Station 2100. It's something DEC made a while ago. Yes. Just because I happen to be familiar with that.
That is a deep cut. Yes. Okay.
And that one did have a serial port card in it. And it's a pretty simple one. It's based on DZ11, which was actually a serial port card back in PDP-11 days. DEC just grabbed it and reused it. So I'm emulating a serial port card for real. Linux thinks it's talking to a real DZ11 card. I am not emulating a SCSI disk drive because that is very tedious. So instead, I'm using the fact that Linux is open source to my advantage here. And I wrote my own disk driver, which I call PVD, or was a partially virtualized disk. And the idea is that I'm using a undefined MIPS instruction to make a call from the emulated world into the emulator itself. And one of those calls I can make is give me a sector or write a sector. And you provide a physical address in your RAM and a sector number. And then the actual emulator does the SD card access. So Linux just thinks it has a very weird disk device that is instantly fast.
And I assume you weren't using Debian 12 because that, I think, released later than your project notes.
Yes. So Debian did finally drop MIPS 1 support. Let me see if I can find out when was the time they dropped it. Because I researched all this and I was writing it and I forgot the actual answer. It looks like, I think it was the last release that they dropped MIPS 1 support. It lasted for a while, but now it is dead, which makes sense. MIPS 1 is long dead. So I think it might be the one before Bookworm that the release I'm using is.
Okay.
The thing is, MIPS had a number of revisions. So there was MIPS 1, then there was 2, 3, then there was MIPS 32, MIPS 64, then there was MIPS 32 E2, E3, E5, E6. I don't think I skipped any there. There was no 4, at least not that I know of. But anyways, MIPS 1 was supported for a very, very long time, so that made my life very easy. Just grab a rootfs and it all works. The other cool thing there is that MIPS was the last architecture I could find supported by modern Linux, where having a floating point is optional, floating point unit, that is, which is really convenient for emulation because emulating floating point units is a pain in the ass.
When I download a new Linux, which I usually end up with Ubuntu, for all that says about me, I'm sorry. It has a whole bunch of cruft that I don't want. And yet I have trouble getting rid of it because I don't know how everything interacts and because I just don't care. How did you make a Debian distribution that was this small? What did you have to go through to get a clean distribution that didn't have all of the cruft?
There's kind of two parts to this question. So one is Debian has a minimal rootfs, which has none of the graphical stuff. That makes it quite easier.
Why don't I use Debian?
But the other part, you are in fact using it. Ubuntu is based on Debian. Right. But the other part is all this stuff gets started by an init system. And to make this project faster, I actually didn't use the init system. So initially for testing, I booted directly into bash. But that leaves you with too few things to a point where console will not act correctly, and you won't have TMPFS, which will break some applications. So I wrote my own little tiny init system here, which will mount TMPFS and procfs and start a couple of services and then dump you into bash. However, the emulator is complete. You can enable swap an SD card and run proper init, and it will bring up the entire thing, complete with send mail and everything else you might not want. It takes a while, though. So spawning a new process takes a really long time, just because we are still running only at one MIPS. And you'll be amazed how many processes get spawned by even Debian, which is pretty small, starting. At some point in time, I counted a few hundred.
Yeah.
So basically, if you actually want to exec init, which is the command you would use to go properly boot up the whole system all the way up to the proper login prompt and all, it takes a little over an hour.
Oh, okay.
There's just no need to ever do that because my init brings up all you need in order to integrate with compiler, VI, you have a shell. I mean, basically all the parts you would need, you have.
No, that totally makes sense. But I was having trouble with the idea you were booting it all up in a few minutes if you were booting it all up.
Kernel is up. You have a command line. Proc is mounted. Sys is mounted. Dev is mounted. Your compiler works. VI works. Emacs works. And your command prompt works. What more could you need?
But you didn't trim it. You didn't try to get to...
No, just start with Debian minimal.
Okay.
If you don't start they're not hurting me by sitting on the SD card. If I was trying to use a smaller SD card just for some other reason, maybe yes, but 1 gigabyte SD cards nowadays are in fact becoming more expensive than larger ones. So at this point in time, the cheapest SD cards I buy on eBay is 100 packs of 2 gig SD cards for like 40 cents each. So trimming it down to less than 2 gigs made no sense.
part of my brain still has 100 megabyte SD card is probably the largest you're going to get. And I know that part of my brain lives in like 2004, but
I know how you feel.
It's just sometimes I forget that what used to be rare now is common.
We're venerable. That's the word.
That's the word.
I know podcast listeners are probably tired of me saying things from the past, but I remember how much it cost to get a 15 megabyte hard drive in my computer.
Yep, I'm with you there. But nowadays, go on eBay, search for 2 GB SD card. There are people selling like 100 packs of them. They'll come to you in a Ziploc baggie. Buy a couple of those and you're set for projects for life. You never even reuse one. You just stick a card to a project and that's it.
That's a really great idea, actually. Because when I need SD cards, I usually go to some larger vendor and buy, the smallest one I get is 32 gigs. Well, I need, 500 megs for this project, but that's the smallest I can get. So I guess I'll pay the $5 or $10 for that. But that's a much better idea to just stock up with the 2 gigs and forget about it.
I just buy them in 100 packs.
Okay, this is back from 2004. The larger SD cards and their SPI interface didn't used to work well, but it sounds like it's all fine now. That in the intervening 20 years, they became okay.
The larger 2 gigabyte SD cards?
Yes.
No, so maybe what you're thinking of is when we switched from SD to SDHC, a lot of code that supported SD didn't work.
Oof.
But yeah, because the protocol changed. I had some fun time with that back in Palm OS days. But yeah, nowadays they're all HC cards and it's all nice and easy. SPI protocol is still mandated in the spec, so they all do support it. Though there are bugs. There are all sorts of exciting bugs because there are corners of the spec that no one reads quite accurately.
Yeah. I mean, there always have been. It's just which ones they are right now. And which SD cards. Do you end up being reliant on 1 or 3 brands of SD cards or calling out some that don't work?
I just buy whichever ones are on eBay. Okay. And then I have an SD card driver I've been slowly improving since about 2004. It's the one that I initially wrote for Palm OS. So over time, I just improve it. So when I find a card that does something weird, I will add support for that weirdness. And I actually have a stack of SD cards I test with, the more weird ones over the years. Make sure I didn't break any of them, and that's it. So my driver over time slowly evolves to support all sorts of stuff.
Okay.
My latest one was a fake SanDisk branded card that claims to support Command 23. It's optional. You're not required to, but there's a way to query if the card supports it. It claims to support it, but if you send it, it rejects it as invalid. Why? I don't know. It's not a marketing thing. No one cares if you support that command, but claiming to support it and then rejecting it is an interesting thing I've never seen before.
Yes. Okay. I know you didn't want to talk about your day job, and I'm not going to ask direct questions, but does this work at all reflect your day job? Does it contribute to your day job? Is this purely separate?
Well, I mean, I suppose this keeps me sharp so I can do clever things in my day job occasionally, but no one's going to pay me to tinker with microcontrollers all day, I'm afraid.
To be able to minimize Linux in this way, I think you'd be surprised. There are some of my clients have wanted it, and I am not the person for it.
Oftentimes, if someone asks you that question, I think this is called an XY problem, is what the name for this is. When someone asks you a question where an answer may exist, but really you got to wonder why they're asking the question because they probably already headed the wrong way. So if someone tells you, how do I fit a whale into an apartment building? There may be an answer, but first you got to ask them why they're asking the question. So if someone asks you to minimize Linux into a tiny space, almost always the first question you should be asking them is, what are you actually trying to accomplish? Because you're probably going around it the wrong way.
Yes, that is exactly what I usually do. And then
that's our whole job, pretty much, is to ask that question.
Yep.
Yes, and all of the horrible questions after, like, do you want the whale to come out of the apartment building later? Do you want to be able to replace the whale?
The client usually responds with what color they want the whale to be.
Yes. Sorry, Dmitry, please go on.
Oh, no, I was going to say that usually when they ask you for that, what you'll find is they're going to try to run a 5-line Python script they have lying around.
Yes.
Yes, indeed.
I've had some fun experience with that because a really long time ago, I wrote the world's tiniest JVM that fit on microcontrollers. And I've had people actually license it from me for all sorts of very strange reasons.
This is the Java virtual machine, just before we go on. Okay, go ahead.
Yeah, I wanted to see how Java works, so I figured the best way is to write a JVM. So I did. And I wrote one that fits in microcontrollers and like a few hundred bytes of RAM. And I've had some companies license it from me, including one that makes agricultural products. Apparently, there's weather stations for farmers, and they wanted a way for them to program arbitrarily complex alerts to be alerted about. And the way they decided to solve that is by letting them upload a compiled Java class file to this weather station's microcontroller. And they licensed my JVM from me to do that. But, you probably don't need a JVM to
you help them with the whale.
Wind greater than 5 miles an hour and it's raining.
Yeah.
And yet it was the way they wanted to do it.
Yeah.
Okay, so did we mention 8-bit AVRs in Linux? We did, didn't we?
Briefly.
Mm-hmm.
And the boot time there was 6 hours.
Well, that was not speed optimized, actually. That emulator was actually written in C, so it could have been optimized quite a ways in assembly.
Okay.
At the time, it was just a yes or no thing. Could I make it work or not? Once I made it work, I moved on with my life. This time, I actually care about performance, so the emulator's written in assembly.
But that's not the smallest or most venerable processor you have put Linux on.
No, that would be the Intel 4004.
Okay.
A 4-bit microprocessor from 1971.
Yep, that's the one.
Finally, something that predates me.
And this doesn't have 8 megabits of RAM and 1 MIPS CPU.
Well, it does. It still uses the same RAM chip, the 8 megabyte PS RAM. I'm just talking to it over bit-banged SPI that I'm bit-banging out of 4004 at a great speed of 7 kilohertz.
7 kilohertz. Okay.
It's the best I could do. 4004 is not very fast. The fun part there is that the RAM chip, it's PS RAM, so it needs to self-refresh internally. So they specify how long you're allowed to keep it selected over SPI so you don't break refresh. And it said 8 milliseconds, so I spent a lot of time optimizing my 404 code to fit into that 8 millisecond boundary. And after I got it working, I realized I misread the datasheet. It was actually 8 microseconds.
Oh, no.
Oh, at that point,
But it turns out it still worked.
It still worked?
Yes, so the reason the limitation is there is to give it enough time to refresh, because it's designed that you select it, read or write, deselect it, select it again, etc. It's not designed to just sit there deselected for a long time. So it expects to do its own internal refresh in small chunks. But I select it so rarely because I'm running so slowly that it has enough time in between these 8 millisecond selections to refresh itself plenty. So it turns out to work fine.
So 120 hertz, 8 milliseconds? Did I do that right?
Mm-hmm.
Yeah. So what was running at 120 hertz?
Well, so I also did a MIPS emulator on the 404 because once again, MIPS is the easiest thing to emulate. And that emulated CPU runs at an effective speed of 74 hertz.
So it's still booting now.
No, it takes about 5.5 days.
I love it.
Where did you get an Intel 4004?
eBay. I had to beat out some collectors who buy them just because it's the first microprocessor ever made. Most of them just put it on a table and never look at it again. But unfortunately, there are a lot of them, so the prices tend to climb up. The plastic ones are $250. If you want one of the pretty ceramic ones, you'll be paying thousands.
Tube Time, Eric. I think you're familiar with him.
Yep.
He has the 8008 board.
Yep.
Have you run Linux on his exploded?
It's a 6502.
Oh, is it?
Yeah.
He made 6502 out of transistors, yeah.
Right. And so have you run Linux on his transistor board?
That's way too slow.
No, but
well, it wasn't when I thought it was an 80.
no, it's a similar thing as on my to-do list. So the reason I did the 404 thing is after I ran Linux on AVR in 2012, That was basically the record for lowest end machine to run Linux for a very long time.
Mm.
And then in 2023, two people actually beat that record. One person used a smaller AVR, and another one did it on a Commodore 64, which has basically a 6502 processor on it.
Yeah.
So I needed to regain my record. I needed something lower end than a 6502. So I went with a 4004. So
that kind of
that's
sets
why they
the
exploited
floor.
6502. Oh, no, it's not setting the floor. I already have plans for the next ones. My plan is to try to beat this record once every 10 years to give people a chance to beat me as well, since this time someone did. So my next few steps. So next one will be a 1-bit industrial controller Motorola did. It's an
okay.
MC14000B, I think. After that, I'll try to make a board with just transistors. And after that, I'm hoping I'll have time to put together a board with only vacuum tubes.
Run it on ENIAC.
I'll have to put together my own CPU there, since there's not really a mass market vacuum tube-based CPU I can go buy. But the idea is to keep moving this record for lowest end machine to run Linux down further and further, just for fun. Obviously, we're well below the speed where it's practical. On 404, you type ls and you come back 20 hours later to see the directory listing.
Seems like you should be collaborating with museums at some point.
Well, at some point in time, it'll become a museum.
I think about Eric's board and how you can see it light up as it works. And
that would make the 5 days, worth
yeah, it would
watching.
be really interesting.
Okay. Well, so once I get to a transistor-based board, it'll be something similar. But even now on my projects, I literally output the current instruction counter PC to LEDs. So you can literally see Linux boot.
Cool.
When it's going so slow, you can actually notice it. You can look at the patterns of lights and know which part of the kernel it's in. While watching it, I learned to recognize the common things like memory zeroing function. I know what that looks like in LEDs now.
I didn't... Oh, that's... Is that on the 8-pin Linux?
No, that's on the 404-based one.
Okay.
The 8-pin one is too fast. The whole point was that one had to be interactive.
Yeah.
If you could see how fast the instruction counter is moving, it would not be interactive.
Have people come to you and asked you to build the 4004 one for them?
I've built 2 more, one for a friend and one for a paying customer who wanted one. I tried to set it up as a kit that people could actually order, but the companies that make kits pushed back on it with very legitimate concerns that it would be very strange to sell half a kit, because you could get the board and the modern components, but no one's going to buy you the original components. You have to go and scour eBay for those.
Yeah.
And that would be a very strange kind of kit. And at the same time, we couldn't really go and source them, A, because it's a huge capital expenditure, and it's hard to predict the sales, but also there's no guaranteed supply.
Yeah.
Some days eBay has supplies of 4289, and some days it doesn't. So basically now it's just, here's the design files, go buy the parts and put it together. I know of at least a few people currently building one of these boards.
You mentioned earlier that you limit yourself to 2 projects until they're written up. And offline, you mentioned that you didn't really enjoy writing. Why do you bother? I'm not discouraging you. You do a great job, and I'm really glad you do it.
The number of people who have reached out to me over the years and told me that reading about my projects encouraged them to get into embedded or encouraged to get better is worth the results of that. There is a shortage of people doing low-level software. You can get a whole CS degree nowadays without ever touching assembly or even C, which is terrifying, because all these people who think the world runs on JavaScript don't realize someone has to write their JavaScript VM. And getting people into embedded is sort of one of my hobbies. And this is how you do it. You do it by trying. It's like riding a bicycle. You can read all the books on riding bicycles you want. Until you get a bicycle and skin your knee a couple of times, you're not actually going to learn anything. And it's the same here. And you learn by doing. And you don't just wake up one day and know how to do this. So having a project you can follow can be helpful. There are people who started my projects and modified them. So my original, for example, Linux on AVR, I know a guy who actually took that, attached a display and an I2C real-time clock to it, and made a nightstand clock for himself that just happens to run emulated Linux. And he wrote a Python app that runs on there that updates the time on this display, which was really, really cool. So I try to make sure that my write-ups are clear for people and that they can be followed. So that plays into part selection, because I hate when I read someone's project and says, "Oh, I used this part that my grandpa left me in his will." Like, okay, great. Where do I get one?
Get a grandpa.
So I try to make sure that my directions are reproducible and the parts I use are something you could at least have a hope of sourcing. And I limit myself to 2 projects because I hate the writing part. It's not fun. Going there with soldering iron is fun. Seeing things work for the first time is fun. Writing isn't. But the way I force myself to do it is I'm allowing myself 2 projects in progress at a time. And a project is in progress either until I've given up on it and destroyed it, to make sure that I can't try to lie and say it's not in progress but come back to it, or until it's been completed and an article about it has been published. So that's basically how I force myself to write. Because if I have 2 projects that need to be written up, I can't start another one until I've written one up.
Do you tend to write as you go, or do you kind of do retrospective
No.
after you finish? Okay.
I take very messy notes as I go, so I can later figure out what I did and when. But like I said, I hate writing. I wouldn't want to spoil the fun of the project with it. Usually it'll take me, depending on the project, a few months to go from start to finish, and then probably about a week or 2 of writing. First, I'll take my notes and try to make an outline. Then I'll go and write very haphazard and typo-ridden article, and then I'll go and spell check it a few times and read through it a few times and organize it, and then add a table of contents. I really hate that part. I tend to do it in times when I have nothing else to do, like if I'm on a plane or if I just have a headache and I can't think right.
You write complex and interesting technical articles when you have a headache and can't think right.
Because when I can't think right, I'd rather go and think about something challenging.
One thing, and this was totally me, I think. I couldn't really find your code. It didn't look like I couldn't find you on GitHub or anything.
That's on purpose.
If I wanted to rebuild this, I saw the list of parts, but how do I get the rest of it?
Oh, every one of my articles has the code down there. So if you look, for example, 8-pin Linux, there's a section that says downloads and use. There's a subsection called the files, and it says the main download is here. And there's a link there that has all the design files, the source code, everything.
Oh,
yes. I am purposefully not on GitHub. A lot of my code is uploaded by other people, but I'm not on there on purpose. I don't really want to contribute to training some ML models with my work. If they want to train on it, they can at least go crawl my website.
And unzip the file.
That's right.
Yep.
If they can't figure out how to unzip it, they're not a human.
It's not.
It's a poor human test. I've been working on implementing a better anti-ML model thing for my website, but I haven't finished it yet.
I wanted to ask, we talked a lot about this project, and I'm about to make a horrible pun, so warning up front.
Preparation for pun.
What was the kernel of this idea? Like, what did this just come to you? Like, I want to attempt this. Were you thinking about it tangentially for another reason, or was it suggested to you? Or
well, so the 8-pin Linux one, the physical size small one, that one was mainly because I was explaining to a neighbor's kid that back in the day you could just go and assemble a computer from a kit.
Yeah.
And I got this look back up to him like I was telling him that we used to go strolling around the main street with Martians. So I decided to try to see if I could recapture some of that in a way that could be appreciated today. Because if I give you a computer kit from the 80s, it doesn't run anything modern today.
Yeah.
So it's not actually believably a computer anymore. Definition has shifted. So I wanted something that can be considered a computer today for some definition of that. And for lower end things like the 404, I just thought it was cool to have this record. And now that someone actually took the time to beat it, I wanted to provide a return challenge. Okay, here's the next thing to beat.
And it's funny, I see where you came to it from that description, but I would have given them a Raspberry Pi, not a Pico. But that's a computer. That's more of a computer than I had through college.
Sure. I mean, absolutely. But you're not going to assemble a Raspberry Pi.
No.
The whole point was I was explaining that there used to be a time when a computer you would buy and a kit you would buy to assemble would produce approximately the same computing power, running the same exact software, more or less. So my goal was to run modern-ish software on something you could actually hand assemble. In theory, with a reflow plate and all the right parts, you could maybe assemble a Raspberry Pi with some effort, but certainly not if it's your second time soldering.
Be more likely to do a bagel board, but yeah.
Yeah, but I mean, the original Apples came in a kit version, I think, the Apple One.
Exactly,
And
yes.
Heathkit had a ton of computers, a lot of Z80-based stuff. So, yeah.
But the actual limitation of 8 pins was my own, just to keep it fun for me.
Yeah, that's
because
really...
realistically, Allwinner makes a chip that has pins, so it's not BGA, it's not even it's not even QFP. They have a real QFN with actual solderable pins, a V3S, I think, that will run proper real Linux. It's an actual ARM core, a modern one, with built-in RAM in the chip. So you can literally plop this thing on a board, sprinkle maybe a dozen parts around it, and you'll have real Linux running on that board. They're very cheap too. So the limitation of 8 pins was just my own, because I decided to lower the requirement from hand solderable to hand solderable as your first soldering project.
So when you embark on the transistor only one, let's not talk about the vacuum tubes for a second. What are you going to invent your own architecture, or?
Yes,
Okay.
The idea is to minimize the number of transistors. So I have to create an architecture that is just designed to run this emulator. Luckily, that does make a lot of things simpler. There are some things you just don't need if you're only going to run an emulator. Don't need memory protection because you can emulate that anyways. And you don't need serial ports because you can use SPI for everything because life is much easier. So yes, the idea then is to write my own architecture, probably 8 or 4-bit one at that point in time. Working with less than 8 or 4 bits would just be tedious.
Yeah.
And more bits will require a lot more transistors. The idea here is I'll be writing it in assembly anyway, so the fact that it's a new architecture is in no way a difficulty.
If I was going to do this, and then you can tell me how wrong I am, because this is not the sort of thing I think about. But if I was going to do this, I would go to the NAND to Tetris book from Shimon Shokin and look at how he has done the transistors to his small assembly.
Yeah.
Because I don't know all of the different assemblies very well. I really only know ARM and some TI. But
that's the perfectly good approach.
And then I think because he actually builds this up the opposite direction you're going, that would be a good way to figure out the possibilities of it.
Yeah, that's a perfectly good approach. By the way, if you like NAND to Tetris, in case you haven't seen it, there's a nandgame.com, which is pretty cool. It's by a different person, but it's basically you start with putting together a NAND gate out of MOS, and then you build other components, and this website will guide you through a set of projects all the way to a working maze-solving robot. So if you haven't seen it, really recommend it. I'm not connected to it anyway, but I recommend it to everyone. It is really, really, really cool.
We've talked about some similar games, but that one's on the web, and it is really fun, especially for folks who are like, okay, but what's under the processor? And it starts out with truth tables, which is kind of painful, but it builds up pretty quickly to, okay, this is how you actually put it all together, and then suddenly you have AND gates and OR gates, and then suddenly you're interpreting things to be much more complicated.
And suddenly you have a robot that solves a maze.
I'll make sure that's in the show notes. Okay. We did not talk about processors. I mean, we talked about PIC16s and their C compiler, their joy of a C compiler, their anti-joy of a C compiler. I mean,
it's not even theirs. It's a third-party company.
And you ended up looking at some Cortex M0s and M0 Pluses, which it was what my brain went to when you first mentioned this. And then I was a bit surprised about the 8-bit or 8-pin chips. Because I'd kind of forgotten that anyone made 8-pin chips. I think I knew at one time because I've had some really tiny projects, but they've gotten, I mean, now you can get 16 pins in a tiny, tiny package, but your goal to solder.
Let me blow your mind. There are actually 6-pin Cortex M0s you can buy.
That's...
All right, so we got power and ground and
Serial
serial.
and SPI.
Well, 4 pins for whatever you want, whether
I
it
guess
be
if
serial
you're
or SPI or whatever else.
careful.
Yeah, and USART. But you do have 2 SPI things, so you do have to have a chip select.
I managed without it in this project.
Did you? How?
Well, so 6 pins after you take away power and ground.
Yeah.
2 for serial port leaves you with 4.
Right.
For RAM, you need SPI. So master out, master in, clock, and chip select. That's your 4.
Right.
Now you have no pins left for SD card.
Oh, but if you put an inverter in there, you're either selecting SPI or SD card.
That was one of the things I considered.
Okay.
The problem is I found some cards really didn't like being selected for a very long time.
Mm.
But also inverters would be an extra chip on the board. I considered it, but I found a solution without it.
Okay.
So SD cards, besides SPI, also support their native SD protocol. It's not as well documented in the open specs, but it's not hard to figure out.
It's not hard to figure out. I have tried to figure it out, but go ahead.
Well, you can go grab my code now.
Yeah.
But the idea is that protocol doesn't use a chip select. It uses 3 wires. But instead of SPI having all unidirectional wires, this uses bidirectional wires. But with that protocol, you can combine it with SPI on the same exact pins. Basically, when you're accessing the memory, the SD card just sees a clock and the command pin is in idle state, which is allowed by the spec. And when you're accessing the SD card, memory sees itself being selected and deselected repeatedly with no command byte coming in, which is also allowed.
Oh, tricky.
So I run them on the same exact wires at the same exact time.
Tricky. Okay.
Okay, this goes along with overclocking in that it would make me uncomfortable to ship a product with this.
Sure.
Well, it's not a product.
No.
Yeah, well, it isn't a product, but also by default, it doesn't overclock very much. But I allow people to do it because it's faster that way.
Yeah.
It doesn't overclock very much. The chip goes 64 megahertz, and you've overclocked it to 150 megahertz.
Well, by default, I think I run it at 130, but yes. So mainly to make things go faster when it comes to processors, it's a question of giving it a higher supply voltage and making sure it doesn't melt itself. So the core in this particular STM chip runs at around 1 volt. There's a built-in regulator. And in order to allow power savings, ST gives the regulator 2 settings. In one, it supplies just under 1 volt, and the chip is allowed to run, I think, up to 32 megahertz. Let me go see if I can find it for you. Yes, up to 16. And then they have a second setting which supplies 1.2, where the chip can run up to the stock 64. And if you try, it'll run at about 80 or so. But some of the older chips with very similar power regulator registers also had another setting which supplied 1.35 volts. So I tried that setting on this chip, figuring ST was probably too lazy to design a whole new regulator. They probably plopped the same one in. And I was right.
Mm-hmm.
So with that setting, the chip will run a lot faster. So a few chips I have here, because obviously it's very individual, can get up to about 180, but every single one ran at 136. So, which is obviously quite a bit faster than 64. So I allow people who put this project together to run as fast as they want and see how fast they can get before it gets unstable. If you have an external supply of vCore, you could go even higher, but obviously in this chip, not enough pins for that. But that's how people overclock like RP2040s and such. Supply vCore externally, you can go even faster.
Add some external cooling and
Yeah.
I'm really uncomfortable with overclocking. I know you've done it with
Why?
your computers, but
I mean, a lot of Intel will sell you a chip that is unlocked specifically so you can overclock it.
but it's. I guess I'm just so engineering design spec mustn't go over.
Well, remember
Well, yes, I'm certainly not claiming that this will run across the automotive temperature range
Right.
and will age properly across a decade. Those are just not design guidelines here. I certainly wouldn't do this if I was shipping a product that's going to run someone's, airplane or something. But this is a hobby project, so faster silicon aging due to higher voltages isn't a problem. And performance in, subarctic winter outside is also not a problem, because I suspect no one's going to try to use this outside in Alaska in February.
I don't know, those Antarctica scientists do get really bored.
They can do it indoors.
Exactly.
And the chip manufacturers, they're trying to hit a spec where they want the chip to survive, even if you put it on a board, don't do any cooling or anything, and
Yeah, no, I know they have to over-engineer it, and then people who want to go outside that span can. It's not how my brain works.
It's not the way you ship a product. But for a hobby project where you only need to make like 2 of these and maybe, a couple dozen people will follow in your footsteps, it's fine. Plus the performance benefits. Think about this. Going from 64 megahertz to 160 is not something you'd really want to leave on the table.
Not for this. No, not when you're talking about a boot time.
Yeah.
And you're right. It's a hobby project. It's for fun. Let's make it fun. And overclocking, I guess, because it's a do not do is kind of fun. On principle.
Just so you know, your computer's overclocked.
Things he doesn't tell me.
Because the BIOS has a thing where you just push a button and it determines, the appropriate clock setting.
I thought the BIOS was just so I could change its little LEDs.
Yeah.
Sorry, that was not true. I'm sorry.
I just wanted to make sure that you knew you were lying to people, that you don't overclock things.
I
have overclocked on your behalf.
Thank you. So you mentioned that you actually chose an ST part, STM32, a G031, which is the M0 Plus.
Yep.
And you had looked at a TI part and a PSOC part as well. But this will work on almost any M0 at this point. There's not a lot of difference between them. No.
So because I'm using basically no hardware peripherals at all, it'll work on anything. I begrudgingly was forced to choose the TI part just because of the speed.
The STM part or the TI part?
Sorry, that's what I meant, yes.
Yeah, okay. Just because it had the highest clock speed.
Yes.
And you begrudgingly chose this because their errata is not as up to date as you'd like.
I am a huge foe of ST Micro. I try to convince everybody who I know is using them not to. I even offer my time for free to companies who are considering switching away from ST Micro to anything else to help them do so.
Really?
We'd like to thank our sponsor, ST Microsystems.
No, they're not our sponsor.
I've beef with them from a number of years ago on a project. They released a part, STM32H7, which was supposed to support external PS RAM, memory mapped in read-write mode.
Oh, right.
And the problem is it was broken. If you enable caching, it would sometimes hang if you ran code from it. If you disable caching, some writes would sometimes get lost or write neighboring bytes. I tried to show them, and even with a demo, they basically denied the issue was there. Then I found a workaround for the issue, and I was able to complete my project. And then a few months later, they came back and said, hey, we have a customer who is experiencing similar issues. Can you tell us the workaround?
You've got to be kidding me.
As soon as you guys admit that the chip is broken, and that's basically as far as that went. So the chip remains broken. I still haven't told them what the workaround is. But basically, if people are out there knowing that their chips are broken and not documenting it, I'm not okay with that. So I've made it my personal mission to try to make sure as few people as possible use ST Micro parts. So being forced to use it was not my personal favorite, but it was the best part in this particular case. And because I'm using no IP on there at all except the actual core, there was very little chance of hitting an errata because they don't design the ARM core. ARM does.
I'm trying to think which processors I've used that were fresh that didn't have some errata that they then denied and later came back for.
I recommend RP2350 to anybody doing anything nowadays that needs an ARM core or even a RISC-V core. I'm a huge fan. The documentation is great. The support forum has actual people from Raspberry Pi answering questions, and these things are really, really fast.
And the hardware abstraction layer is beautiful.
That I wouldn't know, I'm afraid.
My favorite thing is when the chip vendor says, oh, wow, you found a new problem. Thank you for telling us, when they've already admitted it to somebody else separately.
Yeah, it's like we don't talk to each other.
Yeah.
Yeah. That was what I was thinking of. Okay, well, I think we are about out of time, but I wanted to know if you wanted to say anything about DEF CON.
Nah, I think that's already played out.
Okay.
They've said everything they want to say. I've said everything I want to say. everyone has already made up their mind. I think that's over.
Do you think you will be attending in the future?
I never attended DEF CON before this event. I'm not usually big on conferences. I went just to make my appearance. I don't think I have any reason to do that again.
Okay. Dmitry, do you have any thoughts you'd like to leave us with?
More people should get into embedded. It's fun, and I think that it's going to be a very good career going forward. Everyone who's worried about LLMs taking over their jobs should go ahead and try to get one of these coding LLMs to spit out some useful embedded C code for you. It's like having a very enthusiastic three-year-old help you in your wood shop. You're mostly just very, very scared of the results. I don't think that's going to change. So it's fun and it'll be a good job. So anybody who wants to get into embedded, please do. Please encourage everyone else you know as well. We need more people who understand how things actually work.
Fully endorse.
Our guest has been Dmitry Grinberg, hardware hacker. You can find his website at https://dmitry.gr. And I will have links in the show notes.
Thanks, Dmitry. That was great.
Thank you.
Thank you to Christopher for producing and co-hosting. Thank you to Dennis Jackson for the introduction. Thank you to Mauser for sponsoring the show. And thank you to our Patreon listener Slack group for their continuing encouragement of our book discussion. Finally, thank you for listening. You can always contact us at show@embedded.fm or hit the contact link on Embedded FM, where the show notes also live, as well as the transcripts. And now a quote to leave you with. From Cory Doctorow. It's the stupid questions that have some of the most surprising and interesting answers. Most people never think to ask the stupid questions.